So when it comes to quadratic equations, we should know what the general shape looks like. Quadratic equations could look like parabolas. So that is an example of quadratic function. Parabolas may open upwards or they open downwards. Regardless if they open upwards or downwards, they do have some physical properties. Every single parabola either has a maximum or minimum. So in the left example, it has a minimum. In the right example, it has a maximum. We call this special point the vertex. I know I did a quick sketch. There's no coordinate system. I didn't plot any points. But the theory is, or the idea is that quadratics, they are always symmetrical with each other. You can fold them over like a book. You can fold them over the axis of symmetry. And the idea is that the axis of symmetry always runs through the vertex. So every quadratic equation will produce one of these two pictures. Well, what is a quadratic equation? Quadratics can come in various forms. We're only going to talk about two forms today. We have standard form. And that is the classic thing that pops into everyone's minds when you think of quadratics. This is the quadratic equivalent of y equals mx plus b. It's just so common. And that is ax squared plus bx plus c. It's standardized, it's nice, neat, and clean, it looks uniform, it looks pretty, but it's sort of useless in terms of actually getting information out because, well, I can't read any information. I have to do extra math. Contrast that with vertex form. Vertex form of a quadratic looks something like this. F of x equals a times the quantity x minus h squared plus k. Now, vertex form, it looks a little bit more complicated, but it's nice because it gives you information. It actually outright tells you what the vertex is. So in this particular setup, the vertex is always located at h comma k. So, as you guys can see on our agenda, one of our objectives for today is if I give you standard form, I expect you guys to be able to go to vertex form. If I give you the left, I expect you to go to the right. Now, how do we do that? Now, notice, standard form are all loose and separate terms, whereas vertex form, they're all clustered together in one parenthesis squared. Mathematically, to go from loose separate terms to a clustered squared is the technique completing the square. Now, some of you guys may be thinking, oh God, it's completing the square. It's the thing that I hate so much from last year. Or you're probably thinking, completing the square, what the heck is that? My teacher didn't teach us that. Regardless of how your experience or feelings are towards completing the square, let me try to boil it down to as simple as possible. Right. So here's the idea for completing the square. Here's the idea. For all quadratic expressions of the form x squared plus bx. Right. Notice I'm only interested in the x terms. When you complete the square, I don't really care what that constant c is. I just care about the stuff that contains the x. The act of completing the square is adding a specific number. What is that specific number? Well, it is exactly half of the b number squared. Well, by doing that, adding b over 2 squared will create a perfect square trinomial. You're probably going, okay, geez, that's great. So what? Whoop-de-doo. Well, perfect square trinomials are always factorable. So that's the idea. That's the big mystery. I know I don't care what your experience of completing the squares has been in the past, but completing the square is just the step here. Adding b over 2 squared. If you can do that, congratulations, you can complete the square. So let's take a look at an example here. So suppose I ask you to sketch f of x equals 2x squares minus 12x plus 13. Now, we talked about this in Unit 2. If we don't have anything fancy, any fancy techniques, yeah, go ahead and just make a simple XY table. So you can totally ignore this entire lesson and just do XY tables all day long. But that takes a long time. I don't want to do that. Let's be clever about it. So the first thing I want to do is convert this guy into vertex form, because that's what the instructions will say in the practice, convert to vertex. I was just too lazy to write it. Now, to do that, I need to complete the square, but notice the setup. I can only do completing the square for an x squared plus bx. It doesn't say 2x squares, 5x squares, 1/2 x squares. It only works for a single x squared. In our problem here, we have a 2. So I need to get rid of it. Well, naturally, to get rid of things, you just divide it out. But I don't have an equation here, so I can't simply divide it out. Instead, we do division's cousin, which is factoring. Now, you're probably going, but Mr. Vo, that's not going to work out because 13, I can't factor out a 2, and that is true, right? I can't factor a 2 evenly from a 13. But notice, again, completing the square, you only care about the x terms. I do not care about the regular number. So when I factor out a 2, I'm only going to factor it from the pieces that have an x. So factoring out 2 from the x terms gives me an x squared minus 6x. Deliberately leave a gap, close the parentheses, and then we didn't do anything with this 13, so just drop them down. Right? So that's the first thing I would do. If I want to complete the square, just focus on the x terms, ignore the 13. Now let's do the actual completing the square. So the idea is we want to add half of the b number squared. B number is the number in front of the x. So half of 6 is 3, 3 squared is 9. I hope that's not too crazy. If you guys can divide by 2, and if you can square, congratulations, you can complete the square. Not too bad. Yes? All right. So here's the pre-cal level, though. So you guys should have done that in Algebra 2, but this is the extra raising the bar here. We physically wrote plus 9. Right? I took my pencil, put it on my paper, and I physically wrote a plus 9. However, notice how the plus 9 is within the parentheses. Mathematically, that plus 9 has to be multiplied by 2. 2 times 9 is 18. So although physically we wrote a plus 9, mathematically, we added a plus 18. So I'm going to let you guys think about that for 10 to 15 seconds. Physically, we wrote down plus 9, but mathematically, that plus 9 is playing the role of a plus 18. You guys okay with that idea? Yeah. Right. Now, what we've done here is we've made the function imbalanced. I can't just willy-nilly add plus 18. So this technique is called adding a 0. You change the appearance of an equation by adding something, but then immediately undoing it. So if I added 18 by writing a plus 9, I have to undo it by doing the opposite of adding 18, which is minus 18. That right there, that entire 2 steps, plus 9 minus 18, is completing the square. Let you guys digest that for a second. Please let me know if you're confused at all. All right, and then the rest is just do math work, like factor, add, subtract, so on and so forth. So again, the whole point of completing the square is that this guy here is now factorable. The cool thing about completing the square is you don't have to think about factoring. It's always whatever that variable is, whatever that symbol is, half of that number, parentheses squared. Every single time you complete the square. Variable, sign, half the number squared. And then, of course, plus 13 minus 18 is a minus 5. There we go. Voila, we've done it. We wrote it in vertex form. The reason why I like vertex form is because I can read what the vertex is. I don't have to do any extra crazy math. I don't have to break out a calculator. I don't have to use Desmos. I can just read that the vertex is opposite of this number, comma, whatever that number is. So it's 3, comma, negative 5. How does that help me with the actual instructions? Sketch. Well, I'm still going to do an XY table, But instead of, playing Battleship, instead of guessing where the vertex is, I know I can start at 3, -5, right? And the trick is, don't make life hard on yourself. Pick x values that are close to your vertex. So if my vertex is at x = 3, I might use 4 and 5, or I might use 2 and 1. I could use 0 as well. But the idea is you want to stay as close to your vertex as possible to make your picture easier. So I'm just going to use 2 and 1 because I don't know. I like small numbers. Who knows? And then take these x values and plug it into the x in your function. So substitution, I'm going to assume that we all know how to do it. So I'm going to fast forward through it. I'm not going to spend a lot of time. So that's 1 squared is 2, -3. So 1, 2, 4, 8, and that's a +3. So plot it, go home, be happy. So let's see, my y values aren't that too big, so I don't know. Let's do a 8 by 8 maybe. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And so you plot it. 3, -5. 2, -3. 1, 3. And you're probably going, well, that's not a full parabola. Well, we only plotted half of the branch. But the idea is that every parabola's axis of symmetry always goes to the vertex. Well, if my vertex is 3, -5, then automatically I know the other points of my function because I just mirror image it over. So I know that this point is guaranteed to be on my parabola. This point here is guaranteed to be on my parabola. All I did was I just took those black points, mirrored it over, and then we have the full function. Easy peasy. Although the example in our notes didn't ask for it, the questions on the practice will ask for it. Now that I have the graph staring at my face, we can do the same analysis that we did in Unit 2. What is this domain? Oh, I can see that it goes forever to the left, it goes forever to the right. So the domain has to be all real numbers, -infinity to +infinity. What is the range? Ranges are the y values, so you look bottom up. This is just a visual thing. We can see that it starts here on the bottom and it goes forever on top. So what is this y value here? -5. So clearly I know that the range is -5 and it goes forever up to +infinity. Does this graph have a max or a min? It has a minimum. Yes, that was not a yes or no question. Clearly we can see it has a minimum. It's right here. So remember, it has a minimum value. If I use the word value, I want the y value of -5 at, if I'm asking what the location is, that's the x value. Right? So I can clearly see that this function has a minimum value of -5 at x = -3. So that's it. That's a full problem from start to finish. If I give you an equation, I expect you guys to be able to tell me everything about it. Tell me the vertex, domain, and range, his likes, his dislikes, his favorite color, his least favorite food. If I give you a quadratic equation, you should be able to break down everything about it. Okay? In a nutshell, that's what 3.1 is. However, I will concede a point. I love completing the square. Completing the square is probably one of my favorite techniques to do with polynomials. It's the technique I always go to if I'm solving a quadratic that's not factorable. However, in my 8 or 9 years of teaching, I've learned one thing. Kids don't like math. And completing the square is not everyone's favorite thing. For whatever reason, dividing by 2 and squaring is hard for you guys. There is technically an alternative way to convert into vertex form. So completing the square, this thing here, this example, is sort of like the traditional way to do it, the formal way to do it. It's the nice clothes you wear to show off at a party. If you really don't care what you look like, if you don't care about impressing your friends, there is an alternative method. So we'll do the same example. We're not going to graph and all that stuff. We'll just set up the equation. There is an alternative method for vertex form, though. Believe it or not, there's a straight formula. There's a formula that will just give you what you want every single time. For parabolas only, there is a formula to figure out the axis of symmetry. Now, how does that help us with graphs? Well, the idea is that the axis of symmetry always goes through the vertex. So this formula will always give you the x-coordinate of your vertex. And this is the formula. For any function f of x equals ax squared plus bx plus c, the x-coordinate of your vertex is always negative of whatever your b value is over 2a. Always. So let's do the same example. Right? Or rather, we'll look at it. We're not going to solve it completely because we already did. But let's just do the conversion at least. So same example, 2x squared minus 12x plus 13. Let's at the very least convert this into vertex form. And let's pretend this is test day and, oh my goodness, I forgot how to complete the square. I'm freaking out. How do I do this? Well, it's in standard form. So know that this is A, B, and C. I want vertex form. So remember that our goal is x minus h squared plus k. That's our goal there. Well, notice that h and k are my vertex. Hey, I have a formula for the x-coordinate of the vertex. Let's go ahead and use it. So the x-coordinate of your vertex is equal to negative b, which is negative 12, over 2a. So do some math. Negative of negative 12 is a positive 12 over 4. That gives you a 3. But remember, this formula only gives you the x-coordinates. A vertex is a point, x and y. So not a trick question. You did work. You found the x-coordinate. You need to find the y. They give you a function. What can we do? Just plug it in. So the y-coordinate is just plugging in the 3. 3 squared minus 12, 3 plus 13. And it should not shock you that if you do the arithmetic, what do you get? Negative 5. Right? So the idea is that the x-coordinate of your vertex is h. The y-coordinate of your vertex is k. To write in vertex form, you need h, k, and a, though. Gosh darn it. We need an a. Well, guess what? This a right here is the same as this a. It gives it to you. You're done. You have all the missing pieces. Therefore, f of x equals the a, which is 2, times x minus h, which is 3, squared, plus k, which is a minus 5. So I'll delete that plus and put a minus 5. This is the vertex form of the original problem, which, by the way, I'll scroll back down, which, by the way, matches what we got in the previous example. So the previous example is, again, the formal way to do it. This is the quote right way to do it. This is the haha, I'm going to show off to my friends at this party way to do it. But if you don't care about impressing your friends and you sort of want to do the cheater's version, this alternative method will always work as well. Right. Okie dokie? The last example I had was a word problem. Bless you. And the only reason why I included it is just as a cautionary tale. One of the things that you guys love to do, question? Oh. One of the things that you guys love to do when you're doing a quiz or test is you guys don't read the question. Like, you see an equation, so, oh, I'm going to solve it. I'm going to do everything. I'm going to find the x-intercepts. I'm going to find the solutions. I'm going to factor it. I'm going to put it all on paper and hope one of it is the right answer. All right, that's what you guys do. You guys can't do that, especially in future classes. They're going to mark you off wrong. So please, 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 when it comes to word problems, the x and the y, they have specific meanings. So let's take a look at this example. Caution, it's going to be a word problem, so you might have to write like 2 sentences. Okay. So for example, most cars get their best gas mileage when traveling at a relatively modest speed. So not only does this word problem teaches you math, but it also gives you a good life lesson. Don't speed. The gas mileage. And in this problem, they define your variables for you. They use a capital M for gas mileage for a certain car can be modeled by, and they did the hard work for you. They came up with the formula, so they're going to give it to you. You don't have to figure it out. M of S, right? So don't get freaked out. So instead of f of x, they switch the variables. M of s, same thing. M of s equals -1 over 28s squared plus 3s minus 31. And then give us a domain restriction of 15 is less than or equal to s, which is less than or equal to 70, because we all know that no one drives more than 70 miles an hour. This is not part of the word problem. This is sort of a sidebar. But again, don't get freaked out because of the letters. Normal functions are f of x equals stuff, right? So instead of f, they use a capital M. Instead of x, they use an s. So the m is the output. The s is the input. So instead of x and y, we have s's and m's. So just keep track of the variables in your head. So let's go ahead and define the variables here. S is speed in miles per hour, and capital M is the gas mileage in miles per gallons. This is all info. They haven't asked you a question yet. Here's the question. At what speed do you get the best gas mileage? So first things first, let's actually figure out what the heck they're asking us to do. Now, let's pretend that we're not doing 3.1 quadratic functions notes. So I would first analyze the equation that they give me. It's an s squared, something squared. It's a quadratic. Okay, good. So what is the actual question? At what speed do I get the best gas mileage? Okay. Oh, the function is mileage. So I want best. Doesn't best sort of imply the biggest? So, hey, this is just a maximum question. Maximum of a quadratic? Oh, that is vertex. So there we go. We spent 10 seconds thinking about it. We deconstructed the question into a scary word problem into a relatively simple problem, finding the vertex. There's two ways to find vertex. We can do completing the square, or we can do the cheater's version, just use the formula. Let's take a look at this equation. Oh, that's pretty ugly. That's pretty ugly. Let's just go ahead and use the formula, right? Now, instead of x of the vertex, we don't have x's and y's. We have s of the vertex. So the s of the vertex is -b, which is 3, over 2a, which is -1 over 28. So that's -3 over -1/14. Do some fancy math. You get a positive 42. Okay. And that's the s coordinate of the vertex. What would I have to do to get the other coordinate? Plug it into the equation. But would we even need to do that? The question says at what speed? So do you agree that the question is wanting a speed as an answer? What did we just solve for? We solved for speed. So guess what? That's our answer. I don't need to plug it in. The answer is 42 miles per hour, right? So a common mistake I would have saw students do is they would have plugged it in, got a y value, and gave me a coordinate as an answer. Or they maybe gave me the y value as an answer. Moral of the story, answer the question that is asked. If it wants for speed, you better give me a speed. It's like saying, someone asks you, hey, how fast is that car going? And you say, it's red. Like, they're going to look at you funny. Answer the question that's being asked. Now, if I said, what is the best gas mileage? That's when you plug it in and figure it out. Right? So that's the only reason why I included it, just to include a word problem and to emphasize the fact that, hey guys, When you solve a question, please answer the question that they ask you. Alrighty? But other than that, the main idea is when it comes to quadratic equations, everything you need to know about it is the vertex. If you can find the vertex of a quadratic, it's as if you have the key to unlock the quadratic soul. And who doesn't want that level of control?